Today, we're tackling a problem where you need to find the mean of an array, but with a twist. You first have to remove a certain percentage of its smallest and largest values. How would you approach this efficiently? The problem asks us to calculate the mean of an array after removing the smallest 5% and the largest 5% of its elements. The input is an integer array, and the output should be a double representing the trimmed mean. The core challenge is identifying and excluding these specific elements before performing the average calculation. A naive approach would involve repeatedly finding and removing the minimum and maximum elements. You could iterate through the array k times to find and mark the smallest elements, and then k more times for the largest, where k is 5% of the array length. Each search for a min or max takes linear time, leading to a quadratic time complexity of O(n squared). You'd also need extra space, perhaps a Boolean array, to track removed elements, making it big O of n space. This becomes very inefficient for larger arrays due to the redundant scanning. The key insight here is that when you need to identify the smallest and largest elements to remove, their relative order matters. This immediately suggests sorting. If the array is sorted, the smallest elements will be at the beginning and the largest at the end. We can then easily identify the elements to remove by their index. First, sort the entire array. Then, calculate k, which is 5% of the array's total length. We'll need to remove k elements from the start and k elements from the end. This means the elements we care about for the mean calculation will be from index k up to, but not including, index n minus k. We sum these remaining elements and divide by the count of elements that were included in the sum, which is n minus 2 times k. This approach leverages the power of sorting to make selection trivial. Let's trace this with an example. Suppose our array has 20 elements. First, we sort it. Now the smallest values are at the front, largest at the end. Since 5% of 20 is 1, k equals 1. This means we remove one element from the start and one from the end. So we'll exclude the element at index 0 and the element at index 19. We then iterate from index 1 up to, but not including, index 19. We sum all these elements. For instance, if the sorted array is 1 through 6, with many duplicates, and the first element is 1 and the last is 6, we'd sum everything from the second element up to the second to last. Finally, we divide this sum by the count of elements we actually summed, which is 20 minus 2 times 1, or 18. This gives us our trimmed mean. For our example array, after sorting and removing the smallest and largest 5%, the remaining elements average out to exactly 4.0. This is correct because the extreme values were successfully ignored, and only the central values contributed to the mean. You'll spot this pattern when a problem asks you to operate on a subset of elements defined by their rank, like smallest 5% or largest 10 items. Anytime relative order or selection based on magnitude is a core requirement, consider sorting the array first. It often simplifies subsequent operations dramatically. The time complexity is dominated by sorting, making it big O of n log n, logarithmic time. Space complexity is big O of 1, constant time if sorting is in place, or big O of n if a new array is created. This sorting trick is a powerful tool. Try the next problem where you need to find the kth largest element, same pattern. Don't forget to subscribe for more concise DSA explanations.